Every physical interaction in our universe operates under a strict speed limit. Albert Einstein's theory of special relativity dictates that ordinary matter cannot be accelerated to the speed of light. Breaking this limit reverses the sequence of cause and effect. In relativistic math, traveling faster than light is equivalent to traveling backward in time. This creates immediate logical paradoxes, most famously the tachyonic antitelephone, a device that could receive a reply to a message before the original message was even sent. These contradictions led most of the scientific community to dismiss the idea. However, in the 1960s, a few physicists looked for a specific mathematical loophole. They shifted the question from how a particle could cross the light barrier to what might happen if a particle was created already moving at superluminal speeds. Physicist Gerald Feinberg formalized this concept in 1967. He coined the term tachyon after being inspired by James Blish's science fiction story Beep, which featured a faster-than-light communicator. Einstein's equation reveals the tachyon's strange nature. To maintain superluminal velocity, its rest mass squared must be negative. It becomes an imaginary quantity, the square root of a negative number. Plotted on a graph, a tachyon speeds up as it loses energy, reaching infinite velocity at zero. While a particle with an imaginary mass is unphysical in classical mechanics, this mathematical framework provided a foundation for understanding complex behaviors in quantum fields. Quantum field theory redefines our understanding of matter. Instead of solid spheres, physicists see particles as temporary excitations within invisible fields occupying all of space. Within this framework, the tachyon is no longer a physical projectile. It represents a quantum field with a negative mass-squared parameter. In physical terms, imaginary mass indicates extreme instability. It's the mathematical equivalent of a ball balanced on the peak of a steep hill. This state cannot be maintained. The slightest quantum fluctuation causes the field to roll away toward a lower energy state. Imaginary mass serves as a mathematical diagnostic tool for a highly unstable vacuum. This transition is called tachyon condensation. The field rolls down the potential slope, settling into a stable valley where its excitations become ordinary positive mass particles. This process maintains the laws of causality. Quantum field theory confirms that during this decay, no localized signal travels faster than light. Because field operators at separate points still commute, the tachyon cannot be used to transmit superluminal messages or create time travel paradoxes. This condensation drives spontaneous symmetry breaking, responsible for superconductivity, ferromagnetism, and the Higgs field. Ultimately, this process of symmetry breaking is what generates the physical mass for the fundamental particles within the standard model. Theoretical fields are well established, but what about the original search for a physical superluminal particle? Experimentalists spent decades searching for anomalies. Some of the most persistent data came from tritium beta decay measurements, where the electron neutrino's mass squared frequently appeared to be negative. Physicists remained skeptical of these findings, and that caution was justified in 2011. The Opera experiment famously claimed to have observed neutrinos arriving from CERN at faster-than-light speeds. After months of scrutiny, the researchers found a mundane technical error. The impossible data was the result of a single loose fiber optic timing cable. While negative results cannot prove a particle doesn't exist, the continued lack of verifiable evidence keeps the superluminal tachyon in the realm of speculation.